Yes, okay, first, let me say a few words about this new kind of series of lectures. So the idea is the following. The idea is that, during of course, the pandemic period, it was crucial to have these lectures in order to, compensate for the lack of meeting in person. And, but I mean, somehow, maintaining a steady sort of seminar with like a meeting on a periodic fixed basis, we all think that it's not a good idea. I mean, what we need is to be completely relaxed about the schedule. Could be that, at some point there are talks which are close to each other, but and the general idea is that what we want is a fairly relaxed seminar, okay, in which we can interrupt the speaker, we can ask questions, and so on. And I mean, it's really a great opportunity to have, as our first speaker, to have Jean-Pierre Ramis. I mean, I mean, mathematicians, in fact, of course, they can meet physically, but they very often know each other through papers or articles and so on. And I mean, I sort of met Jean-Pierre through a very beautiful account that he gave in Panorama and Synthèse in 1993, which is called the Divergence Series and Asymptotic Theories. And I really recommend all of you to read it. I mean, it's short, it's not long, it has plenty of stories, like the stories of Stokes, who was able to work during the night because his wife had gone away for. I mean, and it's full of extremely interesting mathematics. And so, I mean, I mean, Jean-Pierre also, has collaborated with Fauvet, Richard Jung, and Thomann some time ago in 2010 about the Stokes phenomenon for the prolate spheroidal wave equation. And I mean, it's a great pleasure to really to introduce him. And the topic of his talk will be a complex analytic approach of the prolate spectrum that I studied with Henri Moscovici. Okay, Jean-Pierre, it's your turn.
Thank you, Alain, and thank you to the organizer of the seminar. Okay, so okay. So first of all, I will briefly recall the works of Alain and Henri. So they discovered a new spectrum for the prolate spheroidal operator of order 0, W lambda in this innocent-looking operator in blue. Yes. This it's formally the Sturm-Liouville operator. It has two logarithmic regular singular points at plus and minus lambda, and an irregular singular point at infinity. For Alain and Henri, lambda is a real positive number. Okay. The classical spectrum is very well known. It's related to the interval minus lambda lambda, and the classical eigenvalue are positive or zero. The new spectrum of Alain Henry is the spectrum of self-adjoint extension which was introduced by Alain in 1998. And because they are interested with analogy with zeta, they consider only mainly the event spectrum. I will consider all the spectrum. This spectrum is discrete. It contains a replica of the classical event spectrum and new negative eigenvalues. And CM uncovered a miracle. When lambda is square root of 2, this negative eigenvalue reproduces the UV behavior of the square of the imaginary parts of the non-trivial zero of the Riemann zeta function. Okay. Okay, this is the paper. 20 years ago, Alain explained me self-adjoint extension and suggests a possible relation of the classical spectrum with the differential Galois theory. And with Frédéric, Françoise, and Jean, I follow his suggestion, and we prove that the classical eigenvalue corresponds to the vanishing of the Stokes multiplier at infinity, or equivalently to a property of reducibility of the differential log group on the field of meromorphic function on the complex plane. And in fact, we discovered after that these results are between the line in the very interesting monograph of Meixner and Schäfke in 1944. This is one of the numerous basic monographs on the topic. An important originality of their approach is that they consider analytic continuation of the classical eigenvalue in the complex domain. I will speak a little bit of that later. OK.
Ok, ça c'est tout à fait lui. Bon, il est qu'au début, hein, regarde ça.
OK. Okay, and more recently with Martin Klimes and Emmanuel Paul, in relation with some works on Pelvé equation, we introduce a notion of special solution of a rational linear differential system. And following this path, I propose a new notion of spectrum for such equations in the complex domain. And it is only based on complex analytic tools, more precisely on the notion of wild mononormal representation that I will explain later. This is related to differential Galois group. The differential group is a Zariski closure of the image of the representation. Today, I will not use differential Galois groups. In fact, the idea of such analytic spectrums, they appear very clearly in the foundational article of Schrödinger and the hydrogen atom, and later on some paper by physicists in quantum chemistry. Okay, in particular in study of linear perturbation of black holes. Okay, the one of interest of the analytic definition of the spectrum is that it gives naturally a functional determinant that is an entire function whose zero are the eigenvalues. This appears in the monography of Meixner and Schäfke. And today I will begin very elementary and will introduce informally the notion of analytic spectrum. I will center on the example of the PROLATE operator, and I will describe roughly the general picture only at the end of my lecture. Okay, so Alain and Henry, they compute roughly the value of their new eigenvalue, the negative even eigenvalues. So here is the beginning of their list. It began with minus 39. Okay, and then they compare with, for lambda equals square root of 2, they compare with zeros of zeta. Here you have the comparison. And I continue the list. And from Alain, some slides of Alain, here are the pictures, the comparison with blue and red, and the three curves. Okay, an important fact is that the W admits two symmetries. It is invariant by x minus x and by the Fourier transform. This is very important for the story. Okay, I use standard Fourier transform. I have a formal version used as explained by and used by Malgrange. That is an automorphism of this Auré algebra. Okay, and I will need some change, so I will replace 2IP by some parameter C later. Okay, so the first miracle in the story is that this PROLATE operator of order 0 commutes with the Fourier transform. It's a specific of the order 0 case. It's no longer true for the arbitrary order case. So I recall briefly the picture. You have the space limitation operator, so, okay, P sub lambda, and the conjugate by Fourier, the band limitation operator. Okay, and then you have the story began with this self-adjoint extension introduced by Alain. It is a unique self-adjoint extension commuting with space and band limitation operators. It commutes also with Fourier, and of course, as a consequence, it commutes with angle operator. And this was discovered by the group around Slepian. The new spectrum is discrete and unbounded on both sides. Its negative eigenvalue are simple, and the positive eigenvalue with a priori it's possible that you have some exception. Later will show that it's not the case. Okay, and an important thing for the story is that the new eigenvalues, the non-classical eigenvalue, they are identically 0 on, or it's minus lambda lambda, not 1. They belong to the Sonin space. Okay, and then if you have an eigenfunction of W lambda, the extension, then the leading term at infinity is this one in the even case and this one in the odd case. As you know, it's not possible to concentrate simultaneously a signal in physical and frequency space, but in some sense, it's possible in the true world. Okay, and this is related to eigenvalues of some convolution operator with a sign cardinal kernel. And the first eigenvalue of this operator are very near of 1. Afterwards, they drop sharply to very small positive values. And if you look at the first eigenfunction, they are maximally concentrated within a finite time interval, space interval. Okay, and the important point is that this integral operator shares its eigenfunction with the PROLATE operator. It's what Slepian calls a lucky accident. Okay. So, you know, everybody knows the operator. It's has this kernel, this sign cardinal kernel, and it's, of course, self-adjoint and compact. It's simply related to the angle operator. The spectrum is discrete. The eigenvalues are positive. Okay, and there is an interesting interpretation of the eigenvalues. They express the concentration of the signal on the interval. It's important what will follow. Okay, this is the picture. Some picture of PROLATE spherical function. I will give better picture later. you see on this example that the concentration is for grid values, the concentration is not so good. Okay, some words about the historical origin of these PROLATE operators. So during the 19th century, Niven studied the conduction of it in ellipsoid revolution. So you look at the Helmholtz equations, and there is a separation of variable for the Laplacian in, it's well known that it exists in 11 system of coordinates. And in such a system, the linear PDE is replaced by a system of 3 ordinary differential equations.
Jean-Pierre, what do you mean by 11 systems?
11 system, you have
11 dimensions.
the classical coordinate, the spherical coordinate, the PROLATE spherical coordinate, the parabolic coordinate, and so on.
But you mean it's one of these 11 systems?
Yeah.
Or- yeah.
Yes, each one is okay. They are okay. So here we use. Oh, excuse me. Okay, so in this case, we use one of these 11 systems is a spheroidal coordinate system, but there are a lot of others.
11.
Excuse me. Oh, I have some problems. Excuse me.
It's okay that you slow down a bit because the rhythm is a little bit fast, I think, yes.
It's too fast?
A little bit too fast, yes.
Okay, so here you have the PROLATE spheroidal coordinates. Oh, I have, excuse me, some problem with not works really well. Okay, so here you have the two systems of coordinates. On the left, you have PROLATE. On the right, you have oblate. So you have separation of variable. We get three functions. Okay, and here you have the trivial trigonometric equation, and then you have two equations, the radial equation and the angular equation, these two equations. And in fact, you have a curious, strange phenomena that you see the two equations are the same. The only difference is the name of the variable. Oh, yeah. Okay, and then the angular radial solutions, they correspond to the same eigenvalues, and the analytic extension on the real line coincide of the variable name, but the difference is that the angular variable has domain minus 1, 1, and for the regular part, it's 1 plus infinite. Oh. I have technical problems, sorry. Be careful, it's completely false in the spherical case. In this case, we have a dissymmetry. Okay, then I rescale the band. I do a change of variable in order to compare W with D, the classical PROLATE operator. And you see you have the W is a particular case. It's the case where this M is 0. In the classical case, M is an integer, is the order. Okay. So I will play with W and also with D.
Jean-Pierre, the fact that M is 0, that means that one is looking at solutions which are invariant under rotations. Huh?
Yes, yes. M is 0, you have this, you know, the fact that the PROLATE commute with Fourier, it's specific to the M equals 0 case.
Sure. Okay.
But Jean-Pierre, how about the Hankel transforms for the M not zero? One of the Hankel transforms, I mean. Can it commute with the non-zero order? I wonder, I don't know.
For M not 0, it does not commute with Fourier.
With Fourier, but there are other Bessel functions which give Hankel.
Yes, perhaps, but I am not able to do something with, with that for the moment, okay? Yeah, so here you have I will use the two notation. So here you have the dictionary of flow notation. Later I will use this parameter tau, and in the picture tau correspond to the time in isomonodromic deformation of Malvé 5. Okay, now we will give a description of the local solution at a singular point. Okay, first at the regular singular point. So at the regular singular point, plus and minus lambda, you have this system of solution. Here you have a convergent power series solution in 1 minus, oh, excuse me, it's lambda. Mistake. But an important point is that then you have a logarithm. So the normalization is that Wronskian is this one. Okay, so now I choose the direction at each regular singular point, and I consider the space solution on the germ of sector bisected by D. You can choose D the real line, left or right, but you can choose also D complex on the complex in the complex plane. By analytic continuation along a loop of the solution, along a loop around lambda, we get a linear automorphism of the solution space. There is a monodromy. It's unipotent, and it admits a unique line of eigenfunction, unique because you have the log. It's not the generic case. And after that, you have the global monodromy. You have three singular points at plus and minus lambda at infinity. And then you look at the loops based at some point. And you follow the solution and get a linear permutation of the solution at this ordinary point. And you get the monodromy representation of the fundamental group of the free whole sphere into SL2. In fact, it's better to consider the group E, that is to add a continuous space, not only loops. Okay, I will explain later, but I remark that a complex number is a classical eigenvalue if and only if the global monodromy group is triangularizable. In order to describe the solution at infinity at the regular point, we need the notion of Borel summability of a divergent power series. So I recall briefly the idea due to Borel at the end of 19th century. So I start with the power series at infinity. So I suppose that you have this Gevrey-1 condition, this inequality. Then I define the Borel transform. And because of this inequality, it is a convergent power series at the origin. So I can, formally, I can write the Laplace transform. And if the analytic continuation exists and satisfy a convenient growth condition, then the true Laplace transform exists. And by definition, it is the Borel sum of the divergent Power series. This sum is asymptotic to the divergent Power series in Poincare sense. So the nicer example, the basic example is the Euler series. And if you specialize at x equal 1, you get the summation of the Wallis series, which was discovered by Euler. Okay, there are some generalizations. And so a variant of the Borel summability, the one summability, can be generalized in a notion of K summability, the parameter. And the next step, more complicated, is a large generalization, the notion of multi-summability. And it is quite powerful because all the Power series solutions of all the analytic differential equations, linear or not, are multi-summable. And you can, in some sense, interpret that geometrically as a branching of solution at the singular point. The idea is already in Stokes' work. Okay, so you can imagine the thing that's corresponding to ramified coverings, a nonlinear version of ramified coverings. And intuitively, an irregular singular point, you must interpret it at a pack of infinitely near singularities. The idea is in Stokes, and it was developed by René Garnier in 1990. Okay, so the application to PROLATE, you have a basis of formal solution at here I introduce a spectral parameter. You have a basis of formal solution at infinity, where this V hat, this Power series, are divergent and Borel summable in some convenient direction. So each one is summable all directions except one. And the possible singular direction on the imaginary axis. So in the singular direction, only one of the Power series is summable, and the corresponding sum is subdominant. It is exponentially flat. And when you move the direction of summation, and when you cross a singular line, the sum can be, it jump, it transforms a new one. It is the Stokes phenomenon as described in Stokes' original style. Excuse me. Okay. So you define the Stokes multipliers. So another factor is the fact that the P star acts on the space of formal solution by rescaling the exponential. So then you get a linear group of automorphism of the formal solution space, the exponential torus. And by definition, this torus, the formal monodromy, and the Stokes multiplier generate the local wild dynamic. Okay. And you can extend and get globally, and you get a global group, and in fact, a global group width. Okay, and now a fundamental idea, in some sense it's perhaps evident. Fundamental idea is that the wild dynamic orchestrates all what we can call the natural spectrum. It will be, for me, it will be an heuristic principle in the main part of the lecture, and I will formalize at the end. Okay. And one of the definition, the possible definition of the classical eigenfunction and classical eigenvalues is the naive definition That is, you ask that the eigenfunction is bounded on the interval minus lambda lambda. And this definition works also in the complex domain. It was a definition proposed by Mexner and Chevke. And the classical eigenfunctions are even or odd. And there is evidently an equivalent definition. You remark, in fact, it is equivalent to say that phi is analytic at the extremity. So, and that's the point that the function phi connects to local analytic solutions. That is a solution, this solution has exactly the solution invariant by the local monodromy. So you have two definitions of the spectrum. You have the naive definition, and you have this new analytic definition of the spectrum. Of course, they are equivalent. Okay, and that also you can consider the thing at infinity. And in fact, the classical eigenfunctions are entire. So you can characterize this entire eigenfunction by the analytic expansion, the dominant term at infinity. So you have another definition of the spectrum. And another equivalent definition is due to Kass-Nelson is by self-adjoint extensions of differential operator. It's a unique self-adjoint extension commuting with the truncation of Fourier Laplace on the interval. Oh, what is, I don't know. Okay, here you have the CM characterization of the eigenfunction, old and new. And here also you have an equivalent definition. Phi is analytic at x at the regular singular point. At infinity, it is the Borel sum of an even formal solution. So also in this case, you have the CM definition, and you have an equivalent analytic definition of the spectrum by summation and analytic connection. So using analytic function, we observe an unified definition of the spectra by connection. Okay, at the end, I will propose a large generalization of this concept. Okay, and if you write a convergent Fourier solution at lambda, here you have this coefficient un. And now you can write a basis at infinity with formal solution with this coefficient Vn. And with François, Jean, and Frédéric, we prove a key relation between the un and the Vn, plus or minus. It is this one. Okay. And Alain Henry derived from this relation the following proposition. Okay. So you have this nice comparison for the Fourier transform. And it's related to the fact that the new eigenfunctions are in the Sonin space. Okay, so in fact, you have a connection between 0 at infinity if you consider the solution with the asymptotic to this function at plus infinity. It's analytic at lambda. And if in the non-classical case, then you have this connection value. This function takes the value plus or minus 1 at lambda. And in the classical case, you have this connection, but now it is dependent on it depends on lambda, but it's related to the concentration of the signal. Okay, so I will decide that the new eigenvalue, the concentration is 1. Okay, so for the eigenvalue of Q, the integral operator, you have three interpretation. Concentration and also connection.
Wait, don't go, you are going a little bit too fast, I think.
Yes.
Yeah. So what you were saying, what are the three? We lost the three interpretation. Yes, three interpretation.
Because you have this, you have this eigenvalue.
This is for the positive eigenvalues. Huh? Yeah.
Yes.
Yeah.
No, the eigenvalue of the integral operator.
Yeah, of the integral operator. Okay.
And the eigenvalue of the integral operators, I explained
Okay.
before, they represent the concentration of the signal on the interval.
Okay.
The L2 norm of the restriction. Okay. But then I explained before, as explained before, here you can, this is the concentration, but you can interpret, you can use that to compute the connection value between infinity and lambda.
Yeah. Okay.
Okay. I don't know if it is classic or not, but anyway, it follows from the preceding result. So we have three interpretations. Okay. So now the picture is like that. You have a special solution at lambda. You see it as an eigenfunction of the monodromy, okay? Because of the logarithm, eigenfunction of the monodromy is the same thing as convergent. So you have a line of solution at lambda.
So wait, so this means that you take the special solution which has no logarithmic divergence, yeah?
Yes, exactly.
Okay.
You look at the monodromy, you turn around, and you look at the eigenfunction of the monodromy.
Yeah.
So in the generic case, you have two lines of eigen.
Sure. Yeah.
So, but because of the logarithm here, you have only one. So you have you get a line of solution, a special solution. And at infinity, you look formally. Formally, you have even or odd formal solution. Okay. So if you choose even, it defines a line of solution. And then by summation, you get a line of actual solution.
Okay.
You have a line at lambda and a line at infinity. And an eigenfunction connects the two lines. Okay? Okay, well, I recall briefly Sonic space. There's a function which vanishes identically near the origin as there as the Fourier transform. Okay. Okay, I recall now what happened with in the classical case. In the classical case, the Stokes matrix in a formal basis of well-chosen basis of solution are these matrices with the same S with which we choose correctly the basis. And then a complex number is a classical eigenvalue if and only if this S is 0. That is, if the Stokes phenomenon is trivial. And now you can look at the Stokes function. It depends of the parameter, the spectral parameter mu, and it depends of the parameter tau. Okay, it's entire on C2 of order less than 1/2, and it is a functional determinant for the classical spectrum. And Mechner and Schäfke prove that the eigenvalues are simple 0 of this functional determinant. In fact, the order is exactly one half, which proves that the spectrum is infinite. Okay, so the results, we have some characterization of the classical eigenvalues. Classical one is the fact that there exists an entire solution. Another is that the local monodromy around infinity is trivial, or its trace is 2, or the Stokes phenomenon at infinity is trivial. Now I look at the extension, the analytic extension of the solution, the convergent solution at lambda, and then this the condition, you have this condition. Now this is 0. Now, in some sense, a geometric condition. The global monodromy group is triangularizable. For people knowing differential Allegro group, you have also two characterizations in terms of differential Allegro groups. And then you have the reducibility of the operator in this non-commutative ring. OK.
Je vais un tout petit peu vite là parce que je veux dire, on n'a pas le temps. On n'a pas le temps de voir toutes les entrées de ta longue liste là que tu viens de nous montrer, qui sont très intéressantes. Voilà.
Yeah, the AMS condition looks like a boundary condition, Neumann or Dirichlet, but
yeah, exactly. Exactly. Is you know, the idea is to replace Neumann and Dirichlet condition by a geometric condition related to the singularity of the operators. This I will jump. Okay, so I change the notation because this is the standard PROLATE notation. So it's a translation of the new notation. Perhaps I can jump.
No, you go really too fast. I mean, you know, we just have the time to look, and then, you know, then it goes. So I mean,
it's a change notation. Replace W by the classical PROLATE notation.
Okay, sure. Okay? No, for the notation change, you mean you already showed this page, but still,
no, you know the difference now is that you have this compression parameter. So
I didn't show it before.
So there is a small change because of change notation. Sure. It is this one, okay?
Before you add plus or minus 1, yeah. Sure. Okay.
Before it was just plus or minus 1.
Yeah.
Okay, so I am interested in functional determinant, I explained before. And I built them by this principle of matching by analytic continuation of special solutions. Okay, so now I can compute. You know, I write the connections formula between infinite plus infinite and 1. And I start with this particular solution at plus infinite. I write the connection like that, and I compute the alpha and beta by Wronskian. It's evident. Okay, and then I get a functional determinant for the spectrum. And in particular, you can use that to numerical computation of the eigenvalues. Moreover, the very interesting property, this functional determinant is entire of order less than 1/2.
Wait, yes. Don't go too fast here. So the W is the Wronskian, huh? This is what
Wronskian. You know, at infinity, you have this particular solution.
Okay.
At 0, you have the solution of the classical solution of Maxner and Schefke. You have the analytic solution and the logarithmic solution. And then you extend psi and you write it at 1.
And you mean the 1 over 1 minus x squared is because of the differential of the log? Or yes, yeah.
because
This is
he's not using the Sturm-Liouville.
the Wronskian
No,
is
but
one of
it's just the differential of the log in his notation.
Yeah, it's just a classical Wronskian.
Yeah. So y1 and y2 are the two basic solutions. Yes. Okay.
Yes.
Very good.
Exactly. Okay, but now an interesting property is that this F, you know, the spectrum, the eigenvalue are the zero of F. And this F has a nice property, an entire function of order less than 1/2.
Mhm.
Okay, and then you know to prove that, you prove that in fact this function y1 is depend analytically of the parameters and with growths of order one like that, but it's also true at infinity. So it was proved with the help of Reinhard Schäfke. Reinhard is the son of Fritz Schäfke. Okay. Okay, so half of the work is due to his father,
This,
and half
this,
of the other half is due to Reinhard.
this function determinant also determines the domain, the vanishing of beta,
In fact, Reinhard and his father,
the
they
domain
write
of the.
only a joint paper. It's about this topic. Okay. So because of the connection, for this case, if you have a non-classical eigenvalue, then you know this alpha. It's this one. So in fact, for numerical computation, you have to find the value such that beta is the spectrum is characterized by this condition. And then the numerical computation, you can control them computing numerically alpha. Okay, here you have the picture, the curves. So you have the alpha and beta. And here you have the odd and the graph of the odd and even eigenvalues. Okay, so here are these computation. You know, in the first column, you have the numerical value of Alain and Henri, okay? This rough eigenvalue. And in the second column, you have our numerical value. Here you have beta, you know, it's very, very small. It must be zero, not exactly zero. And here you have alpha, that is the numerical value of the control parameters.
Jean-Pierre, so what program do you use to make this computation? You use
This one we use all the for this one at the beginning we all the old program of Desir of that was built in the
I see.
80s. Okay, now after I will explain. After when we did that, we ignore a new part of the story that I will explain. But today we have a lot better method of computation. Oh, this was the first computation with Desir.
Yes. I mean, I have to say that the way we were doing it with Henri was the following. We were looking at the solution near the regular singular point, looking at the solution near infinity, and we were looking when they match.
Yes.
But at around 1000. Okay, so of course this was very rough. But okay, it was enough.
It was sufficient for your purposes.
Yeah, for our purpose it was enough, yes.
Sufficient, but
yeah.
So we try to do better. Okay, but with in fact with better numerical tools that we explained, we can draw some graph of the eigenfunctions, and because we have very good numerical tools, we can perform zooms.
Ah, I see.
Okay, so it's new.
Oh.
Okay, so you have the class is the first classical eigenfunction, but now if you look here, in fact, you have very, very small oscillations.
Yes.
And then you can, of course, you know that you have oscillation at infinity, but in fact, the oscillation begin here.
Yeah.
So
but this one, yes, the next one is absolutely great because it shows you Sony in space. Yes.
Yes.
Yeah. Yes.
You have some picture like that.
Yes, but don't go too fast here because it's very important. Because on the right you have the yes. So what you have on the
Here
right?
you are near one. Okay,
Yeah,
so here you have this jump near one.
yeah.
So I perform a zoom here.
Yeah. I see. Okay.
And here is a comparison with the asymptotic at infinity. You know,
I see.
you see that the asymptotic is very good even here, even very near.
I see.
I think it's quite interesting. And now the eighth eigenvalue. Okay. So your eigenvalue is this one. The classical eigenvalue is this one, the eighth. And so in this case, the concentration, you know, this lambda, the eigenvalue of k, of the integral operator, is 1/4.
Mhm.
So you see the concentration now is not so good.
No, it's not so good.
Here you have comparison with asymptotics at infinity, comparison with the blue curve is the eigenfunction, and the black curve is asymptotics. So it is quite interesting. Okay, and then I was there, and then you see that the concentration is diminished, a very small concentration like that, and then you have zooms. And comparison with asymptotics. It's okay?
Yeah.
And then the first negative eigenvalue.
Yeah.
The one corresponding to the first zero of non-trivial zero of zeta. Yes. Okay, so to have a good picture, not here, here it's not so difficult, but to have a good picture here, you need a very, very precise value. I will
Phew,
explain
that's
later.
amazing.
We'll
But
explain
we are
later.
plus 30.
Explain what.
My God.
This, okay, this is, we are sure of that. We explain it. I will
That's amazing.
explain
That's really
later.
great. Yeah.
Okay, so when I return to the general case, for the classical eigenvalue, they prove that the zero of the function, their functional determinant are simple. It's not so evident. It's not so evident. They use the fact that for the classical case, when tau is zero, then you get the Legendre polynomials, the Legendre spectrum. And so, in fact, they interpret the classical spectrum as a deformation of the Legendre spectrum. They use that.
Yeah.
It's not so easy. And our numerical experiment suggests that it is all true for the non-classical eigenvalues. We think it's true, but we cannot prove that. I think it's really difficult. In the classical case, the nth classical eigenvalue is an strictly increasing function of the parameter tau. Okay, you begin with the Laguerre spectrum here, and then you strictly increase the eigenvalue. And we conjecture that you have something similar for the new eigenvalue, for the negative eigenvalues that are strictly decreasing. But a very bad thing is that when tau goes to zero, then all the eigenvalue decrease to zero. It's experimental, but it's true. We have a lot of numerical experiment.
Yeah.
So at zero, you have a degeneration of the spectrum. All the non-trivial spectrum crash on zero.
Yeah, because there is no discrete spectrum.
Excuse me?
Because there is no discrete spectrum
No,
for,
there is no this.
for Legendre,
Okay.
like infinity.
Yes. So the classical situation and the new situation are very, very, very different. So in fact, okay. Okay, some indication about the tools. You say I answer the Alain question. The first computation were done with Maple and Desir, but distribution Maple and Desir. But after that, we changed and we use some package of SageMath, and in particular some tools recently developed Mark Bezarova. And it is really impressive, very impressive tool. But it works on, in fact, on Q only on rational. So we replace, in fact, P by a rational approximation. So in fact, we choose, I don't know, 10,000 exact digits for P. So we are sure it works. Okay. So this is the tools. Okay, now something what preceding was we can write the things. But this I think is new, and for me it was very surprising. So now I will speak of new eigenfunctions for the negative PROLATE eigenvalue. So it's new interpretation of the negative part of the CONNES-MOSCOVICI spectrum. Certainly the charms, one of the charms of B spectrality, and in this case of multispectrality, because there are a lot of, in fact, a lot of different equivalent definition of the spectrum. Okay, and now you will see this new eigenfunction. It's very, very simple, and it allows a very easy and efficient computation of the eigenvalues. And using that, we can prove that the non-classical eigenvalues, CM eigenvalues, are negative. No, you remember that there was a possibility of a finite set of exceptions, but it's not the case. Okay, and an interesting thing is that with this new definition of the spectrum, this definition works for all value of M, in fact, even for complex M, and even to the more general case of confluent eigenfunctions. I will perhaps speak a little bit of this function later. Of course, there is a problem. It's very general, but perhaps this new spectrum could be void. So we cannot prove, we prove nothing, but we made a numerical experiment. And we think it's reasonable to think that it's not the case, that in fact you have an infinite spectrum for all values of M. Okay, as I will explain later, for M integer, perhaps there is a possibility to have some relation with the spectrum in same style. For the complex case, nothing is true. Okay. So the classical PROLATE eigenvalue, as I recall before, was they have a naive definition. They are the bounded solution of the interval -1, 1. And they are real positive. Now I don't consider the interval or the real line, and consider the imaginary axis. And on the imaginary axis, I consider the solution along the imaginary axis, and I define the naive eigenvalues are the mu, such that this operator admits a bounded solution on the imaginary axis.
Jean-Pierre, just a second. So what would happen if instead of saying bounded, you would say square integrable? I suppose it would be the same, no?
The same, yes.
It is the same, yeah. Yeah,
Same.
okay. Because this is something we prefer somehow.
The same. In fact, you have three equivalent. I will explain later. You have a free definition. You have this naive. You have the L2 definition, and also you have this analytic definition. You have exponential decay at infinity.
Exponential decay. Okay, very good. Okay, very good. Exponential decay, I buy. Yes.
Okay, and then we prove that mu is naive eigenvalue. If it is naive eigenvalue, then it is negative. It's very, very simple elementary computation. The eigenspace at dimension 1 is evident. The eigenfunctions are even or odd. It's more less evident. And they admit exponential decay at infinity.
Okay.
For their one. And also we prove that mu is a naive eigenvalue on the imaginary axis if and only if it is a non-classical CM eigenvalue. Okay, so it is a new formulation of your spectrum.
It's better that you stay a little bit on this page because, you know.
Okay, of course.
Yeah.
You see, I start with the idea. We explain the origin of the idea in a moment. But in the idea that I look the naive solution on the imaginary, the naive eigenvalue on the imaginary axis.
Yes. And you mean this is coming basically from the fact that the sine over x behavior is replaced by an exponential behavior.
Yes. I think I will explain later the idea. The idea is I discovered that searching to understand in some sense the geometric signification of the fact that the new eigenfunctions are in the Sonin space.
Okay.
Oh, good.
Okay. It's okay, I can go?
Yeah, we can go.
Okay. So the K is the fact that the non-classical eigenvalue belong to the Sonin space. In fact, it was my starting point. So this is the picture. Okay, so I will reinterpret that. So I use the RD space of I look at the upper half plane and the lower half plane and the two corresponding RD space. And then by boundary limit, you have maps, non-tangential limits like that. And then I look at the imaginary version of the Fourier transform. So you get two functions, one on the lower half plane and one on the upper half plane. And then you have this the RD decomposition of this function, like that. So it's okay. Now, if this phi or equivalent psi belong to the Sonin space, defined by the interval -1, 1, then this function is 0. This boundary limit, this sum of the boundary limit is 0. Okay. Okay, then the function extends on the vertical open band. So, in fact, this, you know, you have this, perhaps I have returned. You have these two Fourier transforms up on the lower half plane and the upper half plane, okay? And you go back. And then this, in fact, these two functions extend analytically, and they are opposite. You know, this is a translation of the fact that the eigenfunctions are in the Sonin space. Is it clear?
Yes.
Okay.
Yeah.
But in fact, these two functions are also sums of exponential formal solutions at infinity. But now it's very interesting because they are the sums of purely exponential formal solutions. That is, in the formal solution, you have only only one explanation, not a combination. You know, you can think as pure waves, in fact.
So what you mean is that instead of having a cosine or a sine, there is just
exactly.
one exponential.
Sine
Yes.
or cosine, you have a combination of two
Okay.
exponentials.
Okay, very good. Yes.
One is plus and one is minus. But here you have only a pure exponential.
Yes.
And if you look at the test, you have two exponential, and one is a subdominant in the lower half plane, and the other one is upper subdominant in the upper. So in fact, your the extension of your new eigenvalue, this new eigenfunction that we discovered, they connect to subdominant solution by analytic continuation along the analytic imaginary axis. Okay, so
Subdominant means it's a negative, it decays at infinity.
it's the exponential decay. Okay, you have two solutions.
Yeah.
One is exponentially small compared to the other.
Yes.
Okay. So in fact, this you can define the thing by you can replace the definition by the notion of analytic spectrum.
Yeah.
Okay.
Yeah, this is a good picture. It's like the analog of the logarithmic solution at lambda and the,
Yes,
the
exactly.
other, yes, the regular.
Okay, and now, so we discover a new eigenfunction with corresponding to the same spectrum. But now, what is the relation between the two pictures? How to recover the CM eigenfunction for the new one? Well, it's very simple. I recall that the notion of boundary value of a function, okay, if you have an open set, cutting the real line, then you have, if you have limits on two sides, by definition, this limit is the boundary value of the function.
Yeah.
Okay, now I do.
No, it's better that you stay on this page a bit because we need to
Yes.
look at it. Okay, so
I
so
can
you
do
have-
that. I can do that.
These new eigenfunctions are the extension of to the full complex plane in a way.
Yes, I look at I start with the naive eigenfunction. And then this naive eigenfunction, it corresponds to power series at zero, solution at zero.
Sure.
It is even or odd. I extend it analytically into the holomorphic function, first along the imaginary axis, but after that on all the cut plane.
Okay.
Okay, so I do perform these two cuts. Okay, and then I can take the boundary value.
Okay.
Then we prove that this boundary value is your eigenfunction.
Ah, very good. Okay.
I think it's a nice picture.
Yes. Yeah, it's what physicists call the Wick rotation. But
Yes, exactly.
Yeah, but then it's a full rotation after that.
Okay, so I can interpret the analytic spectrum as matching the formal power series solution at zero, the sum, and the Borel sum at plus or minus infinity. Okay, and then I get a functional determinant. Its entire, its order is less than one, like that, using the same theorem of Reinhard-Schäfke as I explained before. And so it's a classical determinant for a new classical determinant for not the classical, so the non-classical, excuse me, the non-classical spectrum. Okay, now I return to the numerical computation. So Henri Alain used this matching of oscillating function. I explained this matching, analytic matching before, using Borel summation, but now I have a new method.
Okay,
Some
stay,
time
stay,
ago,
stay on this page. Stay on this page, yes.
you know, a long time ago, my PhD student in Strasbourg, Jean-Louis Callot, proposed a method of description of the Hermite and deform Hermite spectrum and deform spectral spectrum. He calls that opening the curtains. I will explain anyway that there is a relation between, in fact, for when tau is big, PROLATE and Hermite spectrum are very, very similar. You know, the two spectrums, the classical and non-classical spectrum, are deformation of Hermite spectrum.
Okay, but so what you are saying is that with the new method, now is the computation is much simpler and
A
quick.
lot.
Yeah. Okay, very good.
Very quick and very simple. Here is the idea. We start from a Power series solution, you extend it, and you have to check if the sum remains bounded on the half imaginary line. So we use, in fact, a dichotomy method. It's very similar to the counting by the Reb school. If you are close of a naive eigenvalue, then what happens is that, you know, at infinity, you have this subdominant solution which is exponentially flat, but you have also an exponential, another solution which explodes, is exponential growth. So in fact, even if you have near the eigenvalue, what happens is that by analytic continuation, the eigenfunction explodes. Okay, I rotate the picture, and I consider the graphs on the real, half real line. Okay, and then numerically, we observe an explosion. And it's a very sharp explosion, a brutal explosion. The graph looks like a vertical half line. And this vertical half line, it goes up or down. And before there is oscillation. Okay, now I move the approximative value. What happens in that is not this x0 will move. The explosion will move later or before. If the half line, perhaps before it is half line positive explosion, after it's downward, upward, downward. If it is the case, we have crossed the eigenvalue.
Looks like an explosive version of the Weil circle method.
Of the?
Weil circle method, because
Yes,
it,
yes, I think
it explodes instead of just.
yes. Okay.
No, no,
Okay. I will show you.
us the curtain. I mean, yes. Okay, very good.
Okay.
Yes.
So I will show you the experiment. So I use this dichotomy. So in fact, SageMath give a grid certified precision. So you get the geometric picture is in some sense formally is certified. So your intervals, the interval I will show you are sure. Okay, so I begin with the first even negative eigenvalue. Okay, so Alain Henry value is minus 39. The analytic matching value that I showed you before is this one. And then apply the curtain method. Okay, so I choose this approximative value. This one corresponds to this black curve. I look to this green value. Then this curve is the green curve here. So it seems best. So I continue the picture. So I use different eigenvalues, nearer and nearer of the good one. So it is the opening of the curtain, you see? The curtain is that.
I see. Very good. Yeah, it's a bit what I was doing. Yeah, okay, very good.
You see? It's very, very simple idea,
Yeah, sure.
but it works very well.
Yeah.
It works very well because it's quite sharp, the explosion.
Yeah.
Okay,
This
so for the first eigenvalue, you get very easily this
Oh,
interval.
this is amazing precision. Yes. Wow. I see. Wow. Yeah.
Okay. So using this method, you get this picture for the first even eigenvalue. And this is the first odd eigenvalue, the first one. So you have this precision for the first eigenvalue like that. First negative eigenvalue. Okay, then we test with eigenvalue a large rank. I'm 148. So the CM value is this one. The matching is this one. And then I use the curtain. And so you have the curves, the colored curves correspond to these values.
Amazing. Yeah.
You see?
This is amazing. Yes.
Yes, you see the opening of the curtain. Okay, and then we can do better, but we have this value.
And in fact, I suppose you can even do a movie where you see the moving of the curve. Huh?
Yes, I will show you a little bit later. Okay, so we have tested some non-zero value of the M, the PROLATE order M. So apparently there are eigenvalues, and apparently there are infinitely many eigenvalues. So we test with this integer value, and also we test with Mathieu equation for the PROLATE interpretation of Mathieu equation is for M equal 1/2. So apparently there are eigenvalues. So we conjecture that this new version of the spectrum is infinite for all the value of M.
You know, there is a sun in space for, that's why I was asking about higher M different from zero. There is a sun in space for the Hankel transforms.
Oh, perhaps you have to explain that. I don't know.
It's like replacing the Fourier transform with the Hankel transform.
The only thing that I knew is that when M is not zero,
Yes.
then you have two other version of PROLATE by eigenvalue shift.
Yeah.
Then they are exchanged by Fourier. I know that, but I am not able to do something like that. But perhaps you can help me.
If that's all right before.
Yeah.
I don't know. Anyway, it's only conjecture. We are testing. No, we are testing numerically.
Yeah.
And you had
I don't know.
false, right?
I don't know how to replace Fourier.
But when we're doing the homework,
Okay, perhaps we can speak of that later. Okay, some remarks on the comparison of Hermite and PROLATE. Okay, for tau equal 0, the PROLATEs become Legendre. When tau, on the contrary, when tau goes to infinity, or lambda goes to infinity, up to rescaling of the independent variable, the PROLATEs look like Weber or equivalently Hermite. But this limit is very singular. So Mexner and Sheff prove that the semi-classical expression are divergent and so on. But numerically, they are very, very efficient. Okay, so this is a picture. We start from Hermite. We scale the time variable, and then you look at that and you interpret PROLATE as a perturbation of Hermite. You know, the red things are very small. when tau is big.
Yeah.
Okay, now you remark that you can remark that in fact you have the classical Hermite spectrum, but of course you have also another spectrum. You have a spectrum on the real line, but also you have a spectrum on the imaginary line by this weak rotation.
Yeah.
And now, if you compare with PROLATE for tau large, the classical Hermite spectrum looks like the thing looks like the PROLATE spectrum of -1 or minus lambda lambda. And my new spectrum is correspond to the Hermite spectrum on the imaginary axis. Okay, so you know at the beginning you have these two Hermite spectra, and they are symmetric. But then when you perturb and you obtain PROLATE, then you have this symmetry is broken. But it's amusing because one corresponds to the trivial zero of zeta and the other the non-trivial zero of zeta. And in fact, they seems correspond to these two spectrum of Hermite in some sense. Okay, and then we conjecture that in fact the Hermite function for n negative, it looks like the new PROLATE function. We conjecture that the same of Gibbs, the conjecture, we have the same number of zero on the imaginary axis. We check for numerical value. It seems that is true.
Yeah. This is a little bit similar with what happens if you move the PROLATE operator in Fock space. The scaling looks like Hermite, and Hermite looks like scaling. The exchange forms in terms of d by dz, not d by dx. I mean, derivatives with respect to z, but in Fock space, not in.
Okay. And here, so I draw some picture to comparing PROLATE and Hermite. Okay, so I choose the eigenvalue of I rank, and this is Hermite. So for Hermite, I know the eigenvalue, of course, exactly. Okay, so I will show you because I know the exact eigenvalue, I can compare with the curtain method. Okay, so I look at the curtain method with these two perturbations of the correct eigenvalue, you see. And then I move this perturbation, this one. Okay, so you see the curtain open quite slowly. But even if you open very slowly, the curtain, you get very, very precise values. Okay. Okay, now some remarks. It's mainly remarks and conjecture. We can prove almost nothing. So it's about the question of analytic continuation of the eigenvalues. So I remind the case of the quartic oscillator. I look at the quartic oscillator on the real line, and Bender and Woos made some numerical experiment on the analytic continuation of the eigenvalue in the complex plane. That is when this parameter is complex. And they saw experimentally that there are only a finite ramification point, algebraic ramification point, accumulating at infinity. And very nice thing that if n and m have the same parity, then the eigenvalue can be connected by analytic continuation. So the idea is that, in some sense, there is only one even or only one odd eigenvalue. So a lot of people try to prove that. Okay, in fact, it's quite difficult. Finally, it was proved by Eremenko and Gabrielov, and it's really, really difficult. The problem is that you have easily a spectral determinant. But the main problem is to prove that the analytic hypersurface defined by F in C2 has exactly two irreducible components.
Very good.
Bernard Malgrange, a long time ago, proposed me, it was Bernard who gave me indicated me the paper of Remenko and Gabrielov. He was interested in that point, and it proposed a Galoisian interpretation of the business. And you project on C the fiber of the spectrum. You know, when you move the fibers, some fibers are exceptional, they are ramification, and like some eigenvalue. There are multiple eigenvalue. And then you have a fundamental group of the puncture basis acting on the generic fibers. And this Galois group, it acts transitively on each event.
By Galois group, you mean the Galois group of the covering, or?
No, the Galois group of yes, the action of the puncture. You remove the Galois group of the infinite covering, yes.
Oh, the Galois group of the infinite cover. Okay, very good. Yes, okay. Yeah, yeah. You mean this is not the differential Galois theory? This is
No.
Oh, this is just covering story. Yes.
Just covering, naive and
Yeah, yeah. Okay.
naive. But in fact, this analytic continuation of eigenvalue was studied before Banderou. It seems that people forgot that, but Mexner and Sheff, they studied the analytic continuation of the classical PROLATE eigenvalue, and they obtained a lot of interesting results. Okay, with Frédéric, Jean, Françoise, we conjecture that, in fact, the situation is the same from there. Banderou, that is, in fact, there is only one even, only one odd eigenvalue up to analytic continuation.
But what about the negative ones? You mean there is only one?
Oh, sure, I will speak after. So this is, now it is for the classical.
This is for the classical one, yes.
After I will go to the negative. Okay, Frischev proves that it is true. There is this statement is true in the Mathieu case, but this case is very, very simple, exceptionally simple. It's related to algebraic version of Hill equations. So even in the classical case, this question is open. Okay, now about the new eigenvalue, we conjecture that it's the same.
That's
Only
But this one is terribly difficult. So I think
it's like in physics, there is only one electron.
exactly, which was the idea of Wheeler. Yes.
Yes.
It's like the idea of Wheeler. You have only one. So if you compare Wheeler and this business, it's the same idea. So we can also have the same idea for the zero of zeta. Perhaps you have only one zero of zeta.
Only 1 0. Well, if there was only 1 0, it would have been proved a long time ago.
No, it's a proof.
Right.
I don't know. No, I think it's just, I have some ideas. I have some numerical test to begin the story in that direction. It is another story. We speak of that another day. For the new eigenvalues, it's more complicated because of the divergence at infinity. You have some jumps, Stokes phenomena, and it is necessary to deform. It's no longer the imaginary axis. We have deformed into paths winding around infinity. Okay, it's technical, but so now it's the functional determinant is a function of not on tau on C
Set
star.
of log tau. Okay, sure. So
covering.
you have to give tau much more precisely. Yes. Okay, fine. Yeah, that's believable. Yeah.
Okay. Okay.
In fact, yes, it's very natural to have the log of the lambda rather than.
Yes. Yes. Log of lambda.
Yes, yes.
Okay. It's an entire function of log of lambda.
Yeah.
Yeah.
Okay, but so this is the conjecture, but it seems terribly difficult. But we will try to. We are beginning to test a little bit the things, but even numerically, it's complicated. Okay, no, I have not finished, but I will return at the end, but it is an interlude. Now I will speak of a new proposal for a new spectral theory based on complex analysis. So the starting point is the concept of special solution. We elaborated with Martin, Emmanuel, and me, and it was about our works on Pelvet equation. And the starting idea that you can guess with what I explained before, it's terribly simple, extremely simple. Sometimes it can be completely stupid. Okay, but I say it's new idea, but in fact it's not really true. It's not so new because it is between the line in some works. The first example is the classical study of special functions. Among special functions, some are defined by linear ODEs. And it's also idea appear clearly in physical science. Oh, excuse me. So it appears in physical science, in hydrogen, in hydrogen molecule ion, and also in black holes, in the quasi-normal modes of black holes. And a lot of examples like that. The idea is exactly the same. Okay, so I began with a quick reminder of singularity of meromorphic linear ODEs. I limit myself to order two equations, if not, it's quite technical. I put the singularity at 0, and then I recall you that you have regular singular point. Analytic, you have a combinatoric characterization, but you have also analytic characterization saying that the formal solutions are convergent. Generically, you have in general, you have two exponents. Okay, the bad case are resonant case when the difference is integer, and in this case, the log appears like in a PROLATE of order 0, or more generally of integer order. In the generic case, the non-zero case, you have a basis of solutions, and the VI are analytic. And then you have the monodromy, and then you have two distinct eigenvalues. And in this case, you have two eigen lines of monodromy. And at irregular point is more complicated. You have generalized exponent, you have a formal monodromy exponent, and you have an exponential exponent, which is a polynomial in 1 over x or 1 over square root of x. So alpha I is a formal monodromy exponent, not the true monodromy exponent. In general, these formal solutions are divergent, and then you can resum them. Okay, and then the k summation, the k is given by the degree of this polynomial. It is an half integer. Okay. Typical example is Airy equation. Okay, so you have the picture, you have the formal, the monodromy, the Stokes exponent, and the exponential torus. This is the ingredient. Okay, now an heuristic spectral principle. Following Nick Katz in the line of Riemann, Riemann discovered the case of the hypergeometric function case. A functional linear equation is nothing than a Modromy representation. It's the same thing. And more generally, I consider, mimicking that, I consider that a non-necessary function equation is not a Modromy representation, but is a wild Modromy representation. And there is a rigorous formulation with Tanaka category, no matter. Okay, but now if an equation is a representation, or a wild Modromy representation, then you can think necessarily that all the natural spectrum can be defined using only the wild Modromy representation. So that it is what I propose. I think that it appears clearly in the example of the PROLATE case. A more elementary, very simple example is the case of a classical orthogonal polynomial. You can interpret the thing using this geometric picture very easily. Okay, so now the definition, I define distinguish solution lines at each singular point. I do like that. I choose a direction at such a point. I consider the sectorial solution, and there are also a space of formal sectorial solution. Okay, so at a regular singular point, by definition, a distinguishing line of solution is an eigenline of the Modromy. So you have two lines, one line like in PROLATE, or all line in a degenerate case. Nearly equivalent, you can replace the definition by a line defined by a Frobenius exponent. It's not exactly the same, but nearly the same. At an irregular point, by definition, distinguishing line of formal solution is an eigenline of the exponential torus. That is, in fact, a line defined by a purely exponential solution. And a distinguishing line of factorial solution corresponds by summation, supposing that there is not singular direction for the formal distinguishing solution. Okay, so there are, in the applications, there are interesting particular case as line of subdominant solutions in physical application in particular. You have some heuristics. If you compare with physics, purely exponential solution will correspond to purely ingoing or outgoing waves, things like that. Okay, it's clear?
Yes.
Okay. Okay, and then you can extend the business to the symmetric case, the case of CM spectrum. You can add to the singular point the fixed point of the symmetry. In that case, you add 0. So now a distinguished line is a line of even or odd solution. Okay. Now, the definition of a special solution is very easy. It's defined by two singular points with marked directions like that. Then you start with these two data, these two local data. Then a continuous path joining them. You say in the simplest case, this path is a segment, but as explained before, you need in some case more complicated paths. Okay, then you choose distinguished local sectorial solutions. And so it's the analog of Dirichlet-Neumann condition. And the solution connecting them by analytic continuation along gamma. So this is the notion of special solution. It's very, very, I think, it is in some sense rather trivial. Okay, there is a variant, but which jump. Okay, so there are a lot of examples in the theory of special function. You can interpret all the classical orthogonal polynomial at special solutions. More complicated because in function of confluent function. You know, PROLATE is a particular case of confluent functions. A very interesting case is the case studied by Shibuya. He studies the Schrödinger equation with polynomial potential. Then in that case, you have a Stokes vector at infinity. And then he studies the spectrum of Shibuya are defined using special solution. So a generalization of Hermite case. Okay. Okay, so a very nice case is the case of quasi-normal modes of linear perturbation of black holes, the music of black holes. So, in fact, there are particular cases of special solution. Okay, perhaps I can jump that. Okay, now I can define the analytic spectrum. I think it's evident. I start with the same data, 2 points with marked direction, path, distinguishing line of solution at each extremity, and by definition, an eigenvalue, mu is an eigenvalue of this operator, the special solution, which is the corresponding eigenfunction. What is interesting is that in the application, the operator depends algebraically of some natural parameters, and it is interesting to consider the dependence on the spectrum of the parameters. Okay, so you have a generalization of spectra, that is spectral sets and things like that. Algebraic spectrum using Galois differential theory and so on. Okay, so in fact, if you go back to Schrödinger paper, then it clearly has this idea of interpret clearly the spectrum as a spectrum defined in this way.
You know, Jean-Pierre, I know the story about Schrödinger. Apparently, Schrödinger was going around asking to people what is the spectrum of an operator.
Yes.
And then somebody told him, but please go to see Hermann Weyl, and he will explain to you. And then Schrödinger answered, no, absolutely not, because then he would compute it before me.
Okay, anyway, he thanks Hermann Weyl for the guidance of the treatment of the equation. Because in this paper, Schrödinger looks at the equation, the radial equation of the hydrogen atom. It looks using the tool, analytic tool. He complexifies the things, and he uses analytics tools very similar to what I explained for PROLATE. At an infinity, if you look at the things, he discussed the thing, he used the Laplace transform, and it's very, very near of my approach based on Borel summability. The idea is practically the same idea. Only a small technical definition. But it's the same because in the case of hydrogen atom, there is a logarithm, like PROLATE. Okay, but what is there are good news with this analytic definition of the spectrum. There are very nice new properties of invariance. If you compare with the classical theory, it's new. It works because we skip the Sturm-Liouville hypothesis, and we use reformulated or new boundary condition. So these analytic spectra are invariant evidently by Mobius transformation, by S homotopic transformation, that is exponential, for instance, exponent shift, and more generally tensor product by a rational equation of order 1. And it is even more interesting by rational gauge transformation. Okay, for rational system of the Riemann sphere, you have traditional gauge transformation, and there is a less known, but there exists. There is an equivalent version for differential equation, for differential operator, using Aurea algebra, using left and right Euclidean division. Okay, and among interesting rational gauge transformations, there are Darboux transformations, are more generally some intertwining transformation. Okay, so in order to study this spectrum, you can do all this transformation. It's quite nice.
How about Q deformations?
Yes? Excuse me?
Q deformations.
Oh, I am looking of Q deformation. I am working a lot on Q deformation. So I try to look at the picture of Q deformations, but Q deformation, I understand rather well Q deformation of hypergeometric and Q hypergeometric.
Yeah, all these special functions appear in Q deformations too, like in the.
But you know what you need for. I think perhaps my feeling, for instance, if you look at people use a lot confluent in functions for black holes. But I think perhaps there is a picture, a Q deformed picture. So in that case, you need a Q deformed equation. But now it's quite complicated. Technically, it's complicated. Okay. Okay, so it's very useful. In fact, you can prove easily isospectrality using such tools. Okay, this sounds quite good, but in fact, if you compare with the tool you know very well, is a big fall. It's very difficult to prove using this approach that the spectrum is non-void and that for sure it is infinity.
And what about the asymptotic behavior of the spectrum? I mean, is it useful?
No, this is also very, very easy. Oh, perhaps, I don't know. I have to, didn't think to that, but okay, anyway, là, tools are missing. Okay, so other people have to invent tools to improve the things. Okay, perhaps if you are not too tired, I would like to say a word about geometric interpretation of the PROLATE spectra. So I go back to PROLATE for their zero, because we try that and we perform some computation, because from our point of view of analytic spectrum, it was very, very natural. But then we discover a strange thing, that is arithmetic properties. I will show you, I have no, okay, it's an observation, we observe that. I can explain. So the idea is to interpret the PROLATE spectra as pullbacks of algebraic curves on a cubic surface. And we do that using a Riemann-Hilbert map. And then we will observe that on the right side of the Riemann-Hilbert map, so the left side is what PROLATE was, where we work, but the right side, using Riemann-Hilbert map, everything lies above Z. So I recall briefly the character variety. So I began with a well-known case. So I start with a 4-puncture sphere. Its fundamental group is isomorphic to a free group of rank 3. Okay. And then I look at the representation into SL2. Okay. Such representation is defined by free matrices. So the representation, space of representation can be identified with an affine algebraic variety. Okay. The loop, no. And then I quotient the representation by equivalence. If I do that with sets, it's bad. You can get not as of space and so on. So the good notion of quotients are algebraic quotients. Okay, so in particular, you can quotient using the fact that you start from an affine space and that okay, and this is SL2, it's a reductive group. Then you have an algebraic quotient, categorical quotient. It is easy to describe it by hand using trace coordinates on the representation. And then you have local coordinates, that is a trace of the monodromies, local monodromies at a singular point, as the 4 punctures. And then you have these 3 blue coordinates. Okay. And then you get the equation of the character variety. It's a cubic, an affine cubic surface in C3. And then you have the formula. Okay, so everybody knows that. Now consider the little more complicated case. Okay, excuse me. Now I give the same picture, but for the Hein equation, that is the function equation with 4 singular points, and I do the same business. Okay, so to Hein equation, I can associate a point of a cubic surface. This is the Riemann-Hilbert map. Okay, and there is the best formulation is with logarithmic differential systems. It's a little bit different. Okay, the cubic surface, generically, it has 24 lines. There is a triangle at infinity. And with Martin and Emmanuel, we prove that the pullback of these 24 lines by Riemann-Hilbert map give line equation with a special solution of the Hein equation for the systems, the Pan-V6 systems. This line corresponds to special solution with very specific asymptotic at the singular points. So there is a dictionary between the very old and nice algebraic geometry and very sophisticated asymptotics for Pan-V equation. Okay, now I do that, but I generalize that, but not for Hein equation, but for confluent equation. So I start with 4 regular singular points, and then by confluence, I get 2 regular singular points and an irregular singular point, like for PROLATE. PROLATE is a particular case. And now you can extend the notion of monodromy representation into a notion of wild monodromy representation, adding to the monodromy the Stokes multiplier. And then we can define the wild character variety as an algebraic quotient of the representation by equivalence. We mimic the classical case. Okay.
But when you use the wild ramification, are you still in the context of algebraic geometry? Or?
Yes, the same. You have exactly a quotient of space of affine space of matrices.
Okay.
Same picture. But you can do effective, you can compute the things. And then you can, exactly like I explained before, there are some technical modifications, but not so difficult. You get an affine
cubic surface.
Okay. This X3 is a trace of the monodromy around infinity, and the two other coordinates is more sophisticated. It's not trace coordinate. Okay, now we have this cubic surface. It has You know, at infinity you have a triangle, but now for the preceding case, the triangle it was there are no singularity at infinity, but now there is one singularity at infinity. So the number of lines is smaller, but the picture is the same. We prove that the pullback of these lines give equation with 5 equation with special solution. Okay, now back to PROLATE. In the spheroidal case, in all the spheroidal cases, this parameter is 0, there is a parameter. Here, this parameter is 1. And then you have this equation. And in the order 0 case, it's very easy, and you get this equation. You have this cubic surface, is C-free, and you see now, you see that this equation leaves about Z.
Uh-huh. Okay. Okay. Okay.
Okay. The classical spectrum I explained before is defined by the fact that the Stokes multiplier is 0. And if we translate the thing with this geometry, it's possible because these coordinates can be computed from S. Then the classical spectrum is a pullback by Riemann-Hilbert of the line on the surface, of this cubic surface, which is defined by these two planes.
Mm.
They are defined on Z.
Yeah.
This line, in fact, is a degenerate retangent plane.
Mhm.
Okay, so this is amusing. This is a classical case. And now the CM spectrum. There are some computation, but it's possible to compute the things and to see that the non-classical of the CM part of the CM spectrum is a pullback by Riemann-Hilbert of an algebraic curve on the cubic surface. I've computed, and then you observe that it's derived on Z.
But it's a countable discrete set. So
No, but because you know in Riemann-Hilbert you have two parameters.
okay.
The two parameters you have the spectral parameter mu,
Yes.
and with the other parameter is tau.
Tau.
You have a surface.
Yeah,
So
yeah.
Riemann-Hilbert is the map from this surface to this cubic surface.
Okay.
So when you pull back, you have to cut by a line tau is constant.
Mm-hmm.
Then you get a discrete spectrum. Okay.
But can't you get then the asymptotic properties of the spectrum by looking at this?
Yes, it's possible to.
That's what I was asking
no,
before.
excuse me. I know it's a dream. I don't know. It's no, I
Yeah,
think,
because this is the whole point of the story. You know, the whole point.
no, I think I hope, but
Okay.
I hope it's my conclusion. My conclusion, if you look on the right side of the Riemann-Hilbert map, it's the ideal world of Plateau, the PROLATE equation, and everything leaves about Z. But unfortunately, now we are chained in the cave.
We have to cut the chains.
Because
Yes.
it seems difficult to understand the arithmetic property on this side. But I don't know, it's a dream. Perhaps it could be related with the arithmetic property of PROLATE. I have no idea. The only thing that I can say is that the fact that everything is defined on Z is quite strange. Okay.
Okay.
Thanks.
Thanks a lot. Thanks a lot, Jean-Pierre. Beautiful talk. Yeah.
Jean-Pierre, how explicit are these the formulas for the psi plus and psi minus? I mean, the ones, the new eigenfunctions. I mean,
The new eigenfunction, yes. What is the question?
they are given by extension of some series,
Yes.
Borel, Hamilton and stuff.
Exactly. So, you know, I have to find the slide.
Yeah.
Excuse me.
So
I will show you.
are they reasonably computable in some way? I mean,
Oh, yeah, what you call reasonably computable, but you know, you have this formal solution.
yeah,
This by a computer system, you can compute
oh,
this,
but then you have the series, which
and then you can sum the series. So, but so they are in some sense concrete in some sense.
yeah, in the sense if you can get some approximations, decent
Yes,
approximations.
yes. It's what you know, we use that for.
Yeah, I'm not talking about the boundary value, which gives
No,
the
no, no.
just
But
the
even, you know, even for
plus and minus, the ones which you have around the imaginary axis.
you know, even if you I recall you your computation, so in this computation we match, we look at the formal power series infinity, and
So you use
we have some tools of summation of this Borel summation.
okay, I see. So
It's you know, it's a work in progress. Marc Mezaroba is working with Michel Laudet on this topic that is on to extend the tools of Marc Mezaroba to Rosummation, to Borel Rosummation and to Kerr summation.
okay.
So the story is beginning today it's not yet so good, but they hope to obtain very good tools.
We are all impatient to get the paper, you know.
Yes, that's why I'm asking.
I'm writing it. It's a long story.
Well, that was a great talk, really. I mean, Jean-Pierre,
Yes, yes.
we are so grateful to you. So I think we can.
Thank you very much.
Yeah, did very interesting.
It's really very interesting. So thank you so much. Yes.
Thank you.
Yes, yes.
So are there other questions? Okay, well then we really thank Jean-Pierre for this great talk. I mean, yes, beautiful.
Yes.
Bye-bye.
Bye-bye,
Thanks.
Jean-Pierre, and thanks a lot.
Bye-bye.
Henri, if you can send me some indication of paper about this question of Fourier for the deformation
Yeah,
of.
yes, sure.
Yes,
I will be happy to have. I don't know the topic.
well, I mean, the branch spaces, the best examples are shown in spaces formed with Hankel transforms, which
I can
instead of
definitely.
Instead of Fourier transforms, which vanish on an interval, like
But somehow, you know, it's a big hope to try to eliminate this crazy denominator where you have this 1/1 minus x squared, I mean, which is really.
no, but you put it in the equation in the
Anyway, you can send some
the
reference.
Sturm-Liouville form, and then you try to. The Bessel functions will do something to that because they.
Okay.
So it could be that you
I
know
am very, very interested. Yes. It could be.
it could work for
Work, it could work, yes.
yes, for arbitrary M. I mean,
Yes, it would be very, very
it'd
nice.
be natural, in fact.
Okay. Okay, because you see in the case of the imaginary axis, you see that apparently everything is working very well. So
Yeah.
it must exist a dictionary.
Yes.
Very
Okay.
good. Very good, guys.
Very nice. Thank you.
Thank you.
Bye-bye.
Thank you, Jean-Pierre, and bye-bye.